Continuation of what we did last week. So remember last week we ended on what inverse of matrices, right? And even though it wasn't covered during last week's lecture, it was rather covered during this week's lecture. This just past Sunday's lecture. So I did cover the inverse last week during last week's lab, but then it wasn't really into that much detail. So now we are going to go into much more detail into computing the inverse or calculating for the inverse of matrices and then its relevance, right, in matrix calculations and in machine learning as well. Okay. All right. So let's begin. Let's begin. All right. So at the end of this particular lab session, of course, you should know how to compute matrix inverse, right? Both by hand using that is using just native Python and also with the NumPy library, how to solve linear systems, right? Linear systems of equations, right? Ideally using the matrix inverse, and also to compute determinants because that's what was covered in this week's lecture, right? And also its relevance to invertibility and then area volume change. All right, we're also going to see how we can use matrices as linear maps, and then we'll also visualize some common linear transformations, right? And we'll look at change of basis, and also we'll look at some applications of what we'll do today in machine learning, right? Okay, so let's begin. So matrix inverse. So matrix inverse, right, is just it's similar to inverse of any real or any natural number, right? So for example, you have a number what of value, let's say 3, and the inverse of 3 is what 1 over 3 or 3 raised to the power negative 1. Is a similar concept, right, in matrices, right? If you have a matrix A, the inverse of that matrix is what a raised to the power negative 1, but finding that inverse, right, or calculating for that inverse is way much more different than if you are finding or calculating for the inverse of a normal real number, right? All right. Okay, good. So um any matrix, right? So specifically, you can only find the inverse of a 4 by 4 matrix. Sorry, a 2 by 2 matrix, right? You can only find the inverse of a 2 by 2 matrix, right? And also, if any matrix, right, has an inverse, then we say that that matrix is what invertible, right? All right. So as I said, of course, not just 2 by 2 matrices, but generally square matrices. You can only find the only square matrices can have an inverse, but not all square matrices, right, have an inverse. And as I mentioned earlier, you can only call a matrix invertible, right, when it has an inverse. So if a matrix is invertible, right, then it means that it has a determinant, or the determinant of that particular matrix does not equal to 0, right? Yeah. And also, the relevance of the inverse of a matrix, right, can be seen in when you want to solve a system of linear equations of the most common form ax equals b. I'm sure we are familiar with this form of a system of linear equations, or this form of equation, right? Okay, so matrix inverses have certain properties, right? So the inverse of an inverse, right, or the inverse of a matrix equals that same matrix. The inverse of the product of two matrices equals the inverse of the second matrix equals the product of the inverse of the second matrix and the inverse of the first matrix. And then the inverse of a transpose of a matrix is equal to the transpose of the inverse of a matrix, right? Okay, so now let's see how we can compute the inverse of a matrix, right? Using native Python and NumPy, right? Okay, so let's begin. So there's a certain general formula that you can use for finding the inverse of normal square matrices, right? So that simple formula is simply 1 divided by the determinant of that particular matrix. I'm sorry we haven't gotten to the determinant yet, but I'm already mentioning that. You bear with me. We are just going to base on the fact that you've already been exposed to what a determinant is during the lecture. So we are just going to use the determinant to know how to calculate for the inverse of a matrix, right? Okay. So simply finding the inverse of a matrix, right, follows is done by using a certain equation or formula, right? It's simply the inverse of the matrix equals 1 divided by the determinant of that matrix times the leading diagonal, the entries of the leading diagonal interchanged, and then the entries of the lagging diagonal negated. So basically, what I'm saying is, if you have, so please look in the notebook. I'm going to indicate with the cursor, right? So if you have a matrix, a 2 by 2 matrix of this form, right, 4 7 and 2 6, right, 4 and 6 are in the leading diagonal or the main diagonal, and then 2 and 7 or 7 and 2 are in the minor diagonal. Now, to find the inverse of this matrix A2, right, what you are going to do is to use a certain formula, which is what? 1 divided by the determinant of the matrix. So in this case, it will be a scalar value, right? Because the determinant is ideally a scalar value. So 1 divided by that scalar value will also result in a scalar. So we are saying that scalar, which is 1 divided by the determinant of that matrix, times, so as I said, you interchange the entries of the major diagonal, which is in this case 4 and 6. So 6 will move to the position of 4 and 4 will move to the position of 6, right? And then you negate the entries of the minor diagonal. So 2 becomes negative and 7 becomes negative, right? So you have negative 2. So the new matrix becomes what? 6, 6, negative 2, 7, 4, right? So you multiply that particular matrix that we just formed by the by 1 divided by the determinant of the matrix, and that will give you the inverse of the matrix. So let's see how we can compute this via code. So we have a matrix over here, a matrix A2, and now we are going to extract the different elements from that matrix, right, for the purposes of finding the inverse of the matrix via using native Python or pure Python, right? So we extract 4, which is shown over here, and then we extract 2, which is also shown over here. Then we extract 7, which is, yes, yeah, no, 0, no, no, no. I'm sorry. So okay, yes, this is, yes, yes. So we extract 4. So this is the index for extracting 4 from inside matrix A2, and then this is the index for extracting 2, right, from matrix A2, and this is the index for extracting 7 from the matrix, and then extracting 6 from the matrix. So we extract all those elements from inside the matrix and store them inside variables, right? And now we'll compute the determinants given over here as det equals a times d minus b times c. I'm sure you remember the formula for finding the determinants of a 2 by 2 matrix by now. So it's just the difference between the product of the elements of the major diagonal and the minor diagonal. So it's basically in this case 4 times 6 minus 2 times 7, right? Which is shown over here. Okay, so the next thing to do is to compute 1 over the determinant. But in this case, we've gone straight to the point, right? And then found the other matrix that I said, the new matrix that we are supposed to form, where we interchange the elements of the major diagonal and negate the elements of the minor diagonal. So that's why we have over here D. And in this case, D is 6, right? So 6 has moved to the first spot or the first position in the new matrix, as you can see over here. And then 4 is at the 4, which is also A, is at the position of 6. And then as you can see, 7 and 2 have also been negated, right? And so it's simply dividing each. So that same formula that I mentioned for finding the inverse of a matrix can also be interpreted as dividing each element of the new matrix that we form by the determinant of the actual matrix, right? So which has been shown over here. So the inverse of A2, right, is given by this formula, right? So specifically for a 2 by 2 matrix. So let's run the code and see what the inverse of the matrix is. So it's shown over here. So the inverse of the matrix A is 0.6, negative 0.2, negative 0.7, and 0.4, right? So now let's confirm this. So there's another rule about the inverse of a matrix, right? Any matrix multiplied by its inverse gives you what? An identity matrix. I'm sure by now we know what an identity matrix is. So to actually confirm that what we've computed over here is the inverse of matrix A, we have to do some kind of test, right? That is, we'll multiply matrix A by its inverse, the inverse that we found, and see if we get an identity matrix. So that is done by this function over here, the mat underscore more function, right? And let's see if we actually get um an identity matrix after applying the mat matrix underscore multiplication function, the mat underscore more function. So this is the result, and as you can see, it's actually an identity matrix. So of course, in this case, an identity matrix, right, for a 2 by 2 matrix would be what? 1, 0, and 0, 1, right? That is 1, 0 on the first row and 0, 1 on the second row. So this is your 1, this is 0. So when you compute this on your calculator or anything, you see that it's a value which is very close to 0. When you compute this, it's also 0, and when you compute this, it's ideally 1 because it's 1.000 all the way to the 4, which is approximately 1. So yes, so the inverse that we found, the inverse of A that we found, is actually correct. So now this is the code for finding the inverse of a matrix using NumPy. So of course, we have to use the linear algebra method, right, inside the NumPy library. Of course, that's the method that we use for all our linear algebra computations. And inside that method, we have the inf or inverse method, right, as you can see over here. So we just pass the matrix whose inverse we want to find as an argument inside that method, and then it will give us the inverse, which is given over here. And as you can see, it's similar to when we tried solving for the matrix or computing the inverse of the matrix using the pure Python. So yes. All right, so let's move to the next thing. The next thing is we are going to see the relevance of finding or knowing the inverse of a matrix, right? So as I mentioned, you can use that inverse to solve for an unknown variable, right? In a certain linear equation. In this case, a well-known and popular equation, ax equals b, right? If you want to find the x values, you can simply use the inverse method. And how is this done? So you have to eliminate a from both sides and to leave so that you can leave x standing alone. And how would that be done? By multiplying both sides of the equation by what? A inverse. And this is how, and yes. And so after doing that, yeah, so yes, by multiplying both sides of the equation by A inverse. So after multiplying the right side, so after multiplying the right side After multiplying the right side of the equation by A inverse, you are going to be left with only x, and multiplying the left side, right, you are going to be left with A inverse times b, which is given over here. So this is the solution. This expression over here is the solution for the linear equation if you want to find the unknown variable x, right? Okay, so now let's see how we can implement this using pure Python, right? So ideally, we use a certain method, right? In numerical methods or in linear algebra, we have certain methods that we can use to solve for a certain system of linear equations, right? Which have been converted into matrices, right? So we have a certain method called the Gaussian elimination method, right? Which consists of two main methods, which is what forward elimination and back substitution. Going into this is going to confuse you guys a bit, and because it is somewhat confusing. I'm sure some of you have done numerical methods, so yeah, you may be familiar with some of these methods for solving for systems of linear equation. I'm sure Albert, I'm sure you've come across it before. I'm sure you've come across Gaussian elimination method for solving for a system of linear equations, but we are going to skip all that since we are going to ignore all that or skip all the Gaussian elimination things since you guys might get confused, and we are going to go straight into seeing how we can solve it what using the a NumPy a certain NumPy method, right? Okay, so now let's go into it. So by now you guys know how the computation is done. You know the mathematics behind the specific method that is going to solve for the particular linear equation, right? This is the mathematics, this is the solution for it. And all that the NumPy method is doing is to implement this mathematics in code, right? Okay, so now let's look at the NumPy method that solves it. So we just simply use the solve method, right? And two, you have to satisfy two arguments, right? In that method, right? So there are two parameters that method takes, right? It takes what? First, your matrix, right? Your A matrix, and then it takes your vector of results. It takes your vector of results, which is your B. So remember, AX equals B. So it will take your matrix A, and then it takes your vector B, right? As inputs to the method, or certain parameters, right, or arguments which must be satisfied in the method, right? And then it returns what? Your vector of unknowns, which is your X vector, right? Okay, so this is it over here. You have um you have your matrix A and your vector B. Pass them as arguments inside the solve method, also inside the linear algebra method. So np.linalg.solve, and then you pass them as arguments, and then you'll be given your values, or your values of the unknowns, right, which is the x, and it's shown over here. So as you can see, it is the values are similar or the same as the values that we got when the Gaussian elimination method was implemented, right? Okay, so far, is there any confusion, or does anyone have any question? If everything is fine, you can just give a thumbs up, or you can just react in the chat. Apart from that, if you are facing any issue, just unmute and then bring it to my attention. Hello, so guys, is everything okay? Are you understanding everything up to this point? Would I have to go back and go through some stuff for you to gain some more understanding before I move on? Afeshi Christian, if you can hear me, just let me know if you're okay with what I've done so far. Or Albert, if you're okay, just let me know if you're okay, or if you're facing any challenge, let me know so that I'll know whether to go back or to move on. Anabi, is everything okay? All right, so that's great. That's great. So let's continue. So now, next thing is to move. We are going into the determinants, right? We've already come across it. So now we are now going to delve into what specifically a determinant is, right? Okay, so the determinant, that A, is a scalar function, right? It's a scalar function, as I said. So solving for the determinant of a matrix, right, gives you a scalar value. And in this case, that we are calling a determinant a scalar function, right, of a square matrix. So only square matrices have a determinant. You can only find the determinant of a square matrix. Other matrices, matrices which have an I don't say irregular shape. Matrices which have rows number of rows and number of columns which are not equal, right, do not have a determinant, and hence they also do not have an inverse, right? Okay, so a determinant is a scalar function of a square matrix that encodes volume scaling and invertibility. So simply finding the determinant of a matrix, right, gives you a value, right, which indicates how much that particular matrix was scaled, right? Good. So I'm sure you remember this from the lecture, right? Mr. Siama showed some graphs, right, and showed that the determinant shows you how much the, let's say maybe the area, right, after you plot some well, after you plot some matrix, right, the determinant shows you the factor by which that particular the area of that particular matrix was increased or the volume was increased, right, and also gives us some it also encodes some information about invertibility, right? So remember that an invertible matrix is a matrix that has an inverse. And remember that there was a certain connection, right, between the inverse of a matrix and its determinant, which is shown over here. So if the determinant of a matrix, right, is not zero, then we can say that that matrix is invertible or it has an inverse. So now that's the connection that exists between the determinant and the inverse of a square, specifically a square matrix. So as I said, so now look, it's even stated over here. So if the determinant of a matrix equals zero, the matrix is singular, that is non-invertible. So every square matrix that has a determinant of value or of magnitude zero, right, does not have an inverse. It's that simple. And if another matrix, right, has a determinant that is not equal to zero, then that square matrix has an inverse. Okay, so how do we find the determinant of a simple 2 by 2 matrix? So this is simply done this way. So as I said, is the difference between the product of the major diagonal and the product of the minor diagonal. That is in this case AD minus BC. How do we find the determinant of a 3 by 3 matrix? It's simple. So first, you take the first row, right? Take the first row of that 3 by 3 matrix and then eliminate the column and row that intersect on the first element of that first row, which is in this case A. So you eliminate D and G and B and C, and now you find, now after eliminating those values or those elements, you find the determinant of the remaining elements in the matrix. In this case, what, E, F, and H, I, and then multiply that result by the A. That's the first part. Second part, you go to the, so I said row, I meant column, the first column. So the next part, you go to the second column, right? In this case, the first element in the second column is what? B. So you eliminate the row and column that intersect at B. So the elements that will be eliminated in this case are what? A, C, E, and H, right? Find the determinant. Hello, I think I got disconnected. Can all right, but can you hear me now? All right, that's good. All right, so where did I get? I think I got disconnected when I got to the second column. That's finding the determinant of a 3 by 3 matrix. Should I start from there or I should take everything? Okay, let me just start all over. Determinant of a 3 by 3 matrix. So to find the determinant of a 3 by 3 matrix, you first take the first column, right? So the first, and after taking the first column, you look at the first element of the first column. In this case, is A, and then the row and column that intersect at A, you eliminate the other elements, right, in that row and column. Keep A, and then find the determinant of these four remaining elements in the matrix, which is what? E, F, H and I, right? Multiply it by the A, put that aside, and then you move to the second column, pick the first element in the second column, B, eliminate the elements in the row and column that intersect at B, leaving B, find the determinant of DG and Fi because it becomes a DG and Fi become a new matrix. Find the determinant of that, multiplied by B and negate B. So it goes like this. So if you have a 3 by 3 matrix, right, and you can use this rule to remember where the negative and the positive goes, right? So for a 3 by 3 matrix, it goes like this: positive, positive, negative, positive, negative, positive, negative, positive, negative, positive, right? So I'm sure that may have been a bit confusing, but just think of it like this: negative will be in the middle over here, positive will be in the middle, and negative will be in the middle over here. And every other place, right, will have a polarity opposite to the polarity of the element over here. So as B is negative, A and C will be positive. As E is positive, D and F will be negative. As H is negative, G and I will be positive, right? Good. So you take the second column and do the elimination and then pick D, G, and F. Find the determinant of that, which is given over here, multiply it by the B, and then subtract that value from what you did with the A first, which is over here, and then do the same thing for the third, the similar thing you did for the other columns for the third column, right? So it becomes C times what? C times the determinant of what? DGEH, right? Good. So that's simply how to find the determinant of a 3 by 3 matrix, right? So, what does the determinants? What significance or what geometrical significance does the determinant have? As I mentioned, there is a factor by which areas or volumes are scaled by the linear map represented by A, right? So, we'll be getting to linear transformations, but since it has already been captured in the lecture, right? You can say that a matrix can ideally be represented as a linear transformation, right? Good. So the the polarity of a determinant or the sign of the determinant, whether a determinant is simply negative or positive, right, indicates the orientation of flip, right? Okay. So now we are going to compute determinants using native Python and NumPy. And then the native Python computation for the determinant is okay. We'll do it. We'll do it. Don't worry. Well, it may be a bit confusing because it uses a certain concept which may be unknown to some of you, which is called the LU decomposition or LU style reduction, right? Okay. So I'm not going to go into how that particular algorithm is. I just want you to know that that is the reasoning, right, behind the NumPy method, right, for calculating the determinant of any matrix, right. You also use the LU star reduction, right. So this code that you are seeing over here, right? The pure Python code that you're seeing over here is what goes into finding the determinant, right? Using the dot det method, right? In Python, right? Okay, so of course np dot we are still using the linear algebra method. So np dot linalg dot det, and then you pass in your matrix, right, as an argument, and then it will give you your determinant, which is shown over here as 35, right? And of course, when it was done with the pure Python, it was also 35, right? All right, so let's move on. So let's look at singular or non-invertible matrices. So as a matrix that does not have an inverse, right, it's also referred to as a singular matrix, right? So a matrix is singular or non-invertible if its determinant is zero, meaning that it doesn't have an inverse. So it means that the matrix has linearly dependent rows and columns, right? I'm sure by now we know what this means. The matrix has a row and column of zeros. That means at least one of the rows or columns of that matrix, right, has its entries being all zero. And also the matrix represents a transformation that collapses space. All right. So now um let's see a sample singular matrix, right? And how we can confirm that the different how we can confirm that relationship between the determinant of a matrix and its inverse. Okay. So we have some matrix B, and then we have another matrix C. So it's a zero matrix, right? So that's why we use the zeros method, np dot zeros, and it's a 2 by 2 zero matrix, right? Okay. So as you can see, even from here, you can clearly see that this column, right? Um, this particular column, there are two and four over here, two and four, right? Have been were gotten by multiplying what the first column over here, which is what one and 2 by a factor of 2, right? Meaning that the second column is dependent on the first column. So the two vectors, right? The two columns in the vector, right? Sorry, in the matrix are linearly dependent, right? Which implies or gives us some idea, right, about the nature of that matrix with respect to if it has an inverse or not. So already we've been given a clue that this particular matrix may be non-invertible or singular, right? So now let's try and confirm, see if we can confirm that. So first we try calculating for or finding the inverse of matrix B, right, using the dot inv method. And then and after doing that, since B may be a singular or non-invertible matrix, right, we are going to get some kind of error, right? And it's given over here. So it shows that the determinant. Yeah, so over here we can see that. So first we calculate the determinant of B. Yes, all right. So after finding the determinant of B, we see that what the determinant of B was 0, and already we've confirmed that it's a non-invertible or singular matrix, right? It's that simple. Now let's look at the zero matrix, right? The 2 by 2 zero matrix, right? Calculate the determinant. It says what is 0. Of course, it's a zero matrix. All entries are 0, so of course the determinant is going to be 0, and automatically it is disqualified as an invertible matrix. So ideally, since a zero matrix is non-invertible or similar, so all square zero matrices. Okay, okay, hello, Anabi, can you hear me? Can you hear me and can you see my? Okay, my screen is about to be shared. So when you okay, I'm sure you can see it now. All right, that's fine. All right, so I think I got disconnected immediately after I finished with checking or with the concept of singular or non-invertible matrices. But did you get the whole concept? All right, okay, then we'll move on. So we are moving to linear transformations and geometric maps, right? So geometric maps are simply the linear transformations are simply the foundation of a geometric map, and we'll get into that soon. So now a matrix A represents a linear transformation. That is, T induces a form of transformation, right, from one dimension r to the power into another dimension r to the power m via a certain equation, right? This is what t of x equals ax, right? So in this case, the linear transformation function, right, is what ax, right? That means to transform x, right, you have to multiply x by a certain matrix, what, a, right? So that is how A represents a certain linear transformation, because when you multiply matrix A by this x, you are going to get a result, right, which will exist in a different dimension from the input value x, right? Okay, so a linear transformation T V to W, right? So V is one vector space and W is another vector space. So a linear transformation T between vector spaces satisfies um, certain conditions or certain rules, right? So the transformation of the sum of two um two vectors, right, or two matrices, right, or any two elements, the transformation of the sum of two elements equals the sum of the transformation of each element or matrix or vector, right? Good. So that is for all you envision an element of a certain vector space, right? Good. Okay. So now the next rule is that the transformation, right, of a certain scalar and a vector v, right, equals the scalar multiplied by the transformation of that vector for all scalars. So it's constant, or it's the same for all scalars and vectors that are an element of the same vector space or a certain vector space, right? So every linear transformation can be represented by a matrix, and every matrix represents a linear transformation, because when you multiply a certain matrix by a vector, right, that vector, which may have been in, say for example, which may have been in was the two-dimensional space, will be converted, will be transformed to exist in maybe a three-dimensional and four-dimensional space, right? Okay. So the matrix A is entirely defined by where it moves. That is the standard basis vectors I, which equals 1, 0 and j 0, 1. It basically means that A can be a linear combination of these basis vectors, right? Which we already know. And the transform vectors I prime and j prime become the columns of the transformation matrix A. All right, that is after the transformation is done. Okay, so now let's see how we can apply a certain transformation, right? How we can apply linear transformation in Python code. So let's look at the pure Python implementation. So it's very intuitive and very simple and straightforward, right? Okay, so you have matrix vector. So we've created a function, right, which takes two inputs, a matrix A and a vector V, which will be transformed, right? And then what it simply does is to perform some matrix vector multiplication. It's that simple and straightforward. And I'm sure we know how to multiply matrices and vectors by now. So that's a matrix. That matrix vector multiplication is given by this expression that I've just highlighted over here. So we have our vector A of these entries, and we have our matrix A of these entries, and we have a vector v of these and with these entries, right? And so basically a linear transformation, right, of vector v will be multiplying matrix A by vector v, which is done by the mathvec underscore pi function that we just wrote, right? And the result is what, 3.02 or 32. And now let's see how to find uh, to calculate for to perform a certain linear transformation, right? And using the NumPy or using NumPy, right? So you just create your matrices using the NumPy array, and then you just multiply the two as shown over here. So you just do a underscore np at v underscore mp, and that will give you the results, right, of transforming v by the matrix A, which is also 3 and 2. Okay, okay, so now let's look at certain kinds of transformations, right, or geometric maps, right? So we have what? Scaling transformation. So it's a transformation that scales the x-axis by 2 and the y-axis by 0.5. So if you recall, all this was covered, like there's the specific magnitude of the different entries of the different vectors, right? Sorry, the different matrices that induce some form of geometric or linear transformation, right? Good. So for scaling, right, which is by, let's say, increasing um the magnitude or increasing the magnitude of the entries of a certain vector, right? You just say you want to increase the magnitude of the x component of the vector, right? You just increase the value, right, of the first entry of the first row in the transforming matrix, and let's say you want to decrease the y component, right? Decrease the magnitude of the y component. You want to decrease the magnitude of the y component by, let's say, half. You just put 0.5 over here. So by manipulating these two values, right, it will dictate whether you increase or decrease either the x component or y component of a vector. And now for sharing, the sharing transformation, right? You multiply it by this particular matrix, right? So sharing is like going to do some form of stretching, right, of a particular matrix or some particular group or set of vectors, right? That's what typical sharing is going to kind of stretch. We will see some application of these transformations soon, very soon. And then rotation, right? So in this case, depending on the kind of rotation that you want to do, right? It's so the kind of rotation that you want to do, whether you want to do 90 degrees, 45 degrees, 15 degrees, whether it is clockwise or counterclockwise, is dictated by the values of all entries, right? I'm sure you remember the specific general form of the matrix, that's rotation matrix. I think first entry is cos alpha. That's what I'm referring to. So if you refer to the lecture that was held just this Sunday, you'd get the intuition behind the matrix that induces a certain rotation transformation. And for reflection, right? So reflecting, let's say, a particular set of vectors about maybe an axis, right? And in this case, we are reflecting the vectors about the x-axis. So you just negate what this component, right, of the vector, the first component. If you want to reflect about the x-axis, you negate this and keep this positive, right? And you get a reflection about the x-axis, right? So one, two or more of these transformations or map geometric transformations, right, can be combined. For example, you want to apply both sharing and rotation. You just have to combine the two matrices, right? And then combine the two matrices by addition. Or the best thing to do is to probably apply the transformations in a certain order. Take for example, you want to apply sharing and rotation to a particular set of vectors, right? So first you apply the sharing, then you apply, let's say, a rotation to the result of the shared matrix, right? Or the shared vector. All right. So now let's see the geometric transformations in action. So let's take for example rotation and scaling, right? So as I mentioned earlier, the general expression for the rotation matrix is what given over here. So cos theta sin theta, and negative sin theta, and then cos theta. Yes, so highlighted over here. And then we are also scaling it, right? So we are increasing it by a certain factor, right? Good. So we'll scale. So the first thing, so we are scaling the rotation matrix, right? Then we'll apply that resulting matrix to points, right? So in this case, we are generating some 10 points, right? 10 points for x, and then 10 points for y, and then we'll apply by applying a linear transformation um, computation, right? We'll show the transformed version, right, of these points over here, right? Good. So x and y, and then we combine them together to form what? A matrix. So we combine them over here, x and y over here, to form what? A matrix, right? We combine them over here to form a matrix, and then we come and do the transformation with this expression over here. So now let's run and see the pictorial, how, or let's visualize this transformation. So as you can see in this graph, or in this graph, the original matrix, right, matrix of points, is the blue dots that you can see over here, right? Good. And then the transformed one, or the geometrically transformed one, is what? The red dots. And as you can see, we've rotated and also increased the size, right, of the matrix by scaling it by a certain factor of 1.3, right? Good. So this is simply how to apply the geometric transformations and how they look like. So ideally, the relevance of geometric transformations, right, in machine learning is that they are applied in data augmentation, right? So if you want your machine learning model to be invariable to how the data appears, for example, you have a cat, right? You don't want your machine learning model to think that the cat is a dog when you just turn the cat upside down. What you do is to augment the data of cat pictures by turning some of them upside down, rotating some of them, reflecting some of them about an axis, and using all those augmented images to train the model. So the model knows that even though, right, this picture is turned upside down, it is still a cat. Even though, right, it has been reflected and is looking different from generally what someone would call a cat, it is still a cat, right? So that's the relevance of these transformations. They are used for augmenting data, right? So that a model is invariable to changes, right, which may occur in real world data, right? All right. So now let's look at another example, specifically a shape being a triangle, right? So we are going to create a matrix, right? Which when plotted, right, is going to give us a triangle, right? So in this case, it's a 2 by 5 matrix, right? And we are going to perform some form of transformation on that particular shape, which is the triangle, right? So the original is the blue that you are seeing over here. If this is not a triangle, this is a trapezium. Sorry. So this is a trapezium. So, uh, so let me change the name over here. So it's a trapezium. Trapezium. All right. So trapezium. Control C. Control V. Control Control V. All right. So we have a trapezium over here. Okay, so now let's look how it transformed using a specific transformation matrix, right? So we did two things in this case, right? We scaled the trapezium, we made it look bigger, and we also sheared it, so meaning the we stretched the trapezium, right? Good. So as you can see over here, that's what this particular matrix does, right? So we both sheared and then we scaled the trapezium. All right. So the original is the blue and then the transformed is the red. All right. So now let's move to change of bases. So the theory of change of bases. A change of bases is a linear transformation that converts vectors from one basis to another. So if B is the matrix whose columns are the new basis vectors, then how do we find the old basis vectors? It's simply is the matrix whose columns are the new basis vectors. Then yes, then it's simply by multiplying multiplying the old vectors by what? The inverse of um by the inverse of B. Wait, let me try and understand this well before I. So theory of a change of base is a linear transformation, of course. If you want to change the basis of a certain, let's say, vector space, right? So that converts vectors from one basis to another. So if B is the matrix whose columns are the new basis vectors, then V new, that's the new vector, equals the inverse of B times the old vectors, right? Okay, so now let's see how to implement this via code. So these are your new basis vectors B, and this is a standard coordinate, right? So after changing the so simply in this case, right? So simply the relevance of change of basis, right, over here is that if you have a certain set of vectors that existed previously in a particular vector space that was spanned by a certain set of basis vectors, right? Changing those bases mean that those vectors are going to change, or they'll have images in the new vector space, right? So these are the old vectors, right? So V old is the old vector, and then these B what is the matrix of the matrix of the vectors, right? Which are the basis of a particular vector space, right? So now so ideally you are changing the vector space which is spanned by a particular basis of vectors, right? Okay, good. So that means if V old existed in the old vector space, changing the basis, right, of that particular vector space, right? Change the basis of that particular vector space means that this particular vector V old is going to have an image, right, in the new vector space. So how do we find that new that image of the old vector in the new vector space? And this is simply the expression for doing that. So these are the so let's see how it is done. So it's also a transformation. It's also a linear transformation. So these are your new basis vectors, right, which have been shown which have been placed in matrix form, and this is the standard coordinate that existed in the old vector space, or the vector space that was spanned by the old basis vectors, right? So how do we find the new base vectors? It's simply by multiplying the how do you find the new basis, the new vectors, right, or the new standard coordinates, right? It's simply by multiplying the old one, right, by the inverse of the new basis vectors which are arranged in a matrix. So it's simply the expression. Find the inverse of the matrix and then multiply that matrix by the old vector to give you the new vector, right? That is simply the vector that exists in the vector space that is spanned by the new basis vectors, right? And it's that simple. And in this case, the new and in this case, the vectors in the new basis, as you can see, v in the new basis what 1.333, 0.333. So this is the image of what this old vector in the old vector space, or in the old basis. So yeah, so this is the image. V in new basis 1.333 and 0.333 is the new is the image of the old vector in the new basis, right? Simple. All right, so now let's see the machine learning connection, the machine learning relevance of linear transformations, right? So ideally, linear transformations, right, are mostly applied in neural networks, and matrix inverses, linear transformations, they are mostly applied in what? Neural networks, right? All right. So for a neural network, we have so let me go through all these first. So common applications of linear transformation and matrix inverses and all the things, the concepts that we covered today are in linear in a fully connected fully connected or linear layer. So ideally, a fully connected layer is a component of a neural network, right? And please hold on, give me a second. Who's there? Who's there? Last week, last week. Yes, last week. It was Rick. Which Rick? My patient now. Last week. Still was last week. And daddy said you should come. I wanted to wait all the way after. All right. All right. Okay. So now let's continue. So yeah. So as I said, a fully connected or linear layer is a component of a neural network, right? So neural network consists of certain layers, right? And each layer in a neural network ideally extracts um different features, right, from let's say an image or data of sorts, right? Okay. So ideally, it does this by increasing the dimensions, right, of the image and extracting certain features from it. And mathematically, it is done using a certain expression, which is what y equals wx plus b. Of course, I'm sure this expression is looking similar to what ax equals b. Is similar in a way. So where w is a matrix, right, a linear transformation. So to induce some form of transformation in a particular vector, and the bias b is a translation. So linear transformations form the core of neural networks. Each layer applies a linear transformation, matrix multiplication, followed by a non-linear activation function, right? So other applications of linear transformation inverses in machine learning are the least squares or linear regression, right? And the linear regression is a machine learning, mostly a machine learning algorithm, right? Yeah. And also we have the principal component analysis, right? Then this is ideally used in support vector machines, right? That's also a machine learning algorithm. And also they are used for invertibility and conditioning. So invertible weight matrices behave differently. Condition number affects the numerical stability. All right. So now let's demonstrate an example application of linear transformation, right, in a simple neural network, right? So we are going to create a certain data set with certain features, right? So in this case, we have a data set with certain features X over here. So we have four samples in the data set, and each sample has three features, right? So we are going to use the numpy.random.run n. So it's going to pick certain random integers, right, and create a 4 by 3 matrix for us, a 4 by 3 matrix of values, which corresponds to what, four samples and three features. And then np.random.run n 3 by 2 are the weights, right? So remember that in our previous labs I mentioned that weights are ideally used to give like the level of importance that should be attached to different features in the data, right? And then the bias will also be what, a vector, right? All right. So now let's see the relevance of linear transformation over here. The relevance of linear transformation is what? Multiplying the weights, right, by the matrix of the matrix of the data examples given over here. So we have what? X times W. So now this is the relevance of linear transformation over here. So when you want to attach importance to certain features, right, how do you do that mathematically? Simply by multiplying weights by the data set, right? And we have different weights that correspond to certain rows or that correspond to certain columns, right, of the data. So the columns are what, the features, right, and they will attach some level of importance to the features, and then and then some activation is done, right? So after calculating the z value, right, for a particular training, for a particular data set or a particular training example, right, you are going to um try and see, right, whether certain examples fall inside or outside a certain threshold. And in this case, you are using what, the ReLU activation, right? I can't go to all the details about how the ReLU activation is, but this idea is just to show the relevance or application of linear transformation in neural networks, right? All right. So yes, so these are input matrix, the weight matrix, and then the bias vector, right? And how to compute this is simply a linear transformation that is done on the x vector or the training examples, right? Multiplying them by the weight matrix and adding the result of that to the bias vector, right? All right, so and this is the output. Then we perform some ReLU activation, right? So let's say for example you are doing some form of binary classification, right? Classifying, let's say, maybe some numbers, right? Let's say uh a certain values, right, are characteristic of, let's say, somebody who is predisposed to a heart condition, and another set of values are characteristic of someone who is healthy or without any heart condition, right? Okay, so what the ReLU does is that it's going to convert what this z value of the of each of the um training examples, right? Convert that z value into some value that is either that falls within the range of what, 0 to 1, right? And then it's divided into two parts. So numbers that range from 0 to 0.5, and numbers that range from above 0.5. So maybe we'll say that um features, or sorry, examples with what, a z value less than 0.5, right, are indicative of a heart disease or can be classified under someone who is predisposed to a heart disease. And then examples with a z score above 0.5, right, are someone who is not predisposed to any heart disease, right? Well, this may be confusing, but I'm sure when you begin your project, especially because you are working, and because you are working, you are going to be working on something about heart disease and everything, you may be able to apply neural networks, or even not necessarily neural networks, but maybe a regression model or some simple machine learning model, and then you see the relevance of some of this linear algebra and the relevance of some of these linear algebra concepts in that. So in this lab, we covered a matrix inverses, singular matrices, determinants, linear transformations, change of basis, and we also saw how the linear transformation in a matrix inverses, right, is applied in machine learning, specifically neural networks. All right, so these concepts are very, very important, and they are fundamental to actually understanding how linear algebra is relevant or important to machine learning, and how it causes machine learning algorithms to work and function the way that they do, and also how it affects data transformations. So thank you very, very much for joining the lab session and for following till the end. I hope everything was understood. We still have 8 minutes, so I'd like you guys to voice out if there's something that you may not have understood, so that I can actually take the time to go over that. Hello, Albert, Anabi. Is there something you may not have understood and you would like me to go over? Hello, hello, guys. Anything that you want me to go over, and I'll just go over it. All right, and I guess everything is fine since no one is voicing out any concern or is not understanding anything. So thank you very much for joining the lab session, and I hope to see you guys next. So anyways, good luck with your projects. If you need any help, you can always contact me. I'll be very, very, very happy to help you guys.